get going. These are 25-minute sessions, so I'm going to try and get to this material and leave some time for questions. So I'd like to get rolling here. So I'm Mark Gregotski. I'm in LHG, and this presentation is where we are with respect to our secure data path implementation for set-top box security. And as if people have been following LHG's progress, they'll probably notice that we have made a technology direction change. In previous Connect, we've been talking about a secure memory allocation framework, and since last November, after the Connect in Las Vegas, it was decided to make a change in direction. It was primarily the security working group that had that came to that conclusion, and of course we fully support what SWG does. And so in this presentation, I'm going to talk about, the first part of this presentation is really more about what is being delivered from the security working group that LHG will build upon. And then I'll talk about on the Android media framework, how we will build upon that. Again, it's a fairly brief talk, but hopefully I can cover the bases and cover them adequately. So, as I've mentioned, we had a change in our technology direction. There was an effort to upstream something called Secure Memory Allocation Framework, which had some great work by actually the fellows here, Benjamin Gagnard, but unfortunately just didn't gain enough traction in the open source community. And we started looking for alternatives, and we know there's some new ideas out there, but we looked at what's currently available in staging at this time, which is ION, and we thought that having extensions made to ION in the near term made the best sense. You've got something that's actually being delivered in product. We think that the best thing to do here is try to put efforts into getting ION out of staging and into mainline. So there, just as an aside, there is an ION BOF tomorrow, and there you'll get the latest information on the current efforts to get ION into mainline. But what I'm going to talk about here is the secure data path implementation with the memory allocator, and then the extension or modification to be made to ION to allow us to get what we need in terms of our secure data path implementation for LHG, which then adds the specific DRM. I'll talk about Android and Widevine, but we're also going to use it for our PlayReady work. And so not only on Android, but we plan to use this underlying ION secure data path memory allocator for both our Linux-based work as well as our Android-based work. So again, we will use the work from Security Working Group. There's an assignee, his name is Etienne Carrier, who's been doing a lot of design work on this secure data path memory allocator. There's two components here. One is STP with OPTEE extensions, and then of course the actual ION extension for support of one of their memory pool types, what they call their heap types, to have a secure heap type. So I'll talk about that. So I think this diagram is probably familiar to people who are familiar with trusted execution environments. On the right-hand side, you have everything in the trusted agent space, the trusted execution space, the OPTEE core, the OPTEE trusted applications, and secure processors. On the left-hand side, you have the non-secure space, which is the client application, the T-client API, and then the secure memory allocators. So the way currently right now with OPTEE and global platform, you can set up non-shared memory, and we're looking to extend this to support secure shared memory. But the thing that's important here is that the implementation for secure memory is that the secure memory allocations are done by the RE, the rich execution environment, the non-secure side. So that's where the actual commands to create the secure memory allocated buffers originate from. But the thing that's, of course, necessary is that the non-secure space cannot access the contents of those. So it can orchestrate or set up the, instruct the T to set up these secure data buffers, but it can't access them. So typically for a global platform and OPTEE, and even with ION, people who allocate the space can access it. But here we're having the allocation done in the non-secure REIT to allocate the secure memory, and then it's on the trusted side, the trusted application, that accesses the secure memory. And so the invocation parameters, as they're called, from the non-secure side are fed into the trusted side, and that's where the actual secure buffer resides. So the responsibility is on the non-secure side, the RE, to allocate these secure data path buffers. But then the T is responsible for ensuring that the trusted application is working with the right type of memory, right type of secure memory. And so the security working group has defined a series of OPTEE SDP extensions to the global platform APIs in order to bring this about. And so the trusted app itself in the secure space accesses the SDP buffers through the ARM trust zone using the secure attribute. So really the main point I want to get across here is that in this architecture, the secure data buffers are allocated from the non-secure space, but obviously cannot be, the contents of those buffers cannot be accessed through the secure space. The contents of those buffers are only available in the T. Okay, so as I mentioned, there's a series of OPTEE secure data path extensions that have been defined. There's been a definition for the client application. The OPTEE SDP extension allows conditional applications to invoke trusted applications with parameters referencing secure memory buffers. And this is done by a authorized, or it provides an authorized SDP memory area. So the client application cannot access the secure SDP memory buffers, and the trusted application is the one that works on the SDP buffers with ARM trust zone using the secure attribute. So there's an extension to the T client, everything in that diagram that I showed just previously. In the client application, the client, the T client APIs, and then in the secure side, there's modifications or extensions that have to be made in each component. In the kernel, the OPTEE Linux driver is then responsible for creating the shared memory instance of each memory reference used as provided by what we call these invocation parameters. The OPTEE core obviously has an extension to allow the global platform T specification to allow the trust application to be what is termed SDP aware. So that way they know the trusted application can verify that the memory it's using is in fact secure. So the trusted application itself, the extension here is that it's given some SDP memory buffer parameters such as a memory range, and these are passed into a TA entry point, and then it can verify, and it has the support added to say that yes, this is secure data. So for, again, to repeat, as for a TA to be invoked with secure data path memory references, it requires this support from the OPTEE core to allow it to check the memory reference as being secure. So there's something that like an agent called the Secure Data Path Memory Allocator mechanism that is in the non-secure world, and it manipulates the secure memory reference in the clear. It provides like a physical base address in byte size, and then so we'll be looking ultimately for ION to implement this secure shared memory allocator agent in the non-secure world. As I've mentioned, the ION memory allocator has right now is currently defined heap types, and so it currently registers specific memory pools called heaps and gets allocation from both the kernel and user space. However, none of these currently defined heap types satisfy our requirements for the secure memory allocator, and so we need to allocate a physical region of memory that the allocator can be aware that these are the physical addresses, but it cannot access it. So when Etienne was looking at the design, he found that previously a company, All Winter Technology, had already introduced the concept of a secure heap, and he's built upon that using the same concept. He's renamed it an unmapped heap, since it's basically an unmapped memory allocator driver for ION, meaning that in terms of the kernel space, it can't actually, on the non-secure side, it doesn't see that space because it can't access it. So one of the important things to keep in mind is that when we were working with SMAF, the thing that was important to us in the media pipeline is to be able to work with DMA buff, file descriptors as we go through the media pipeline in the non-secure space. So keeping the DMA buff framework is important, and that's why the ION solution is not really an issue for us in the sense that SMAF provided DMA buff support, ION will provide DMA buff support. So as we build our media framework with particular DRM solutions, the underlying mechanism to provide the secure data buffers being ION-based, as long as it supports DMA buff file descriptors, that's really the piece that was important for LHG. So the fact that SWG is using ION and is compatible with DMA buff, it suits our needs. So I just wanted to set that initial part about how we are now looking at the OPTEE SDP memory, secure data path memory allocation scheme, and then look at an example implementation or design using Android. So with Android, this is just taken from their website, their media framework hardening. In Android 7, they have re-architected the media process. So to improve device security, they broke up the monolithic media server process into separate processes with their own permissions. And part of that was to divide, it used to be media server had everything all under it with all the permissions. They've now separated out the media DRM server process as a separate process. So typically what's happening here in the user space is that you have a media player app. It can be something like an ExoPlayer app or another media player that is exercising it. And you would have the media server process, but now it communicates through the binder IPC mechanism to the DRM server process. And in Android, you allocate these secure buffers so that we have to coordinate what we're doing with the SDP memory allocator such that it's allocating these OMX buffers and providing these secure buffer handles. And so these secure buffer handles are what's passed from the media server process to the media DRM process. And those will be, like as I mentioned before, compatible with a DMA buff requirement. Once you're in the media DRM process, you have the media framework and then the interface to the the DRM component, which can either be like a trusted application in the T, or it can be like a crypto block in the in secure space. But this is how we intend, like on Android, to implement the secure data path. So the vendors have to work with secure buffer handles and then use the binder mechanism to transfer those between the server and DRM processes. So as I mentioned, in Android 7, there is an OMX allocate buffer that returns a pointer to the native handle struct, which contains file descriptors. And there's a new OMX extension that is providing the native handle, and so you can query for this support, and it notifies the implementation to use these native handles. And so we can populate file descriptors in those native handles as we need to support our DMA buff implementation. The thing that's, I think, interesting from an architecture point of view is that the OMX allocate, the buffer allocation using OpenMax on Android is now isolated, which means that possibly other types of mechanisms may be introduced at some point, just speculating that typically when you break apart an architecture and isolate certain things, it maybe gives opportunities to do different things. So we'll see what the folks at Google or Android might do there in next releases. So this is at a high level what we see with the media DRM server and the codec server. So as I mentioned, the media server has these two distinct processes now. And so we have above the trusted execution environment, the OEM crypto host talking to an OEM crypto trusted application. And then those file descriptors are passed as you decrypt into another secure buffer. You then pass that file descriptor to the media codec service, and there could be a codec TA, or it can most likely interface with a hardware codec for hardware decode. And then the last step of this would be an HTTP, something to secure the rendering piece. Either you can go directly to like an integrated LCD, or via HDMI, you would have like HTTP control and potentially have some sort of a trusted application or something that would interface with an HTTP, like bulk encryption process. So that's pretty much what I had, kind of high-level overview. And it's just really to let you know that the direction change we're going with the technology, and we're currently working on working very closely with the security working group and looking at the Widevine integration to implement the secure data path. We want to essentially reach a Widevine level 1 solution, and then the next couple steps is that we have a PlayReady plugin that we've already developed that we would try to get that working. And then on the Linux side, we have a PlayReady implementation, like with a Linux OE build, we have PlayReady, but that uses the things like the Open CDM construct and the CDMI. So again, what's important to us is that underlying secure data path memory allocation scheme can provide the secure buffers, the file descriptors we need, and through DMA buff. Once we're above that, if all of that is working properly, we should just be able to implement what we need. Of course, there's a lot of implementation details to work out with each one of these vendors. They each do their things a little bit differently. Anyway, that's all I had, and are there any questions?
The security buffer scheme you just described, does it apply across Linux Android TV and all the other platforms?
Well, if it's supported in the Linux kernel in terms of, like I said, there's like two components. One is in the trust execution environment, the SDP OPTEE extensions, or OPTEE SDP extensions is one set of extensions for the global platform APIs, and then the other is the introduction of the new ion buffer heap type, the secure heap type, and all of that is in the kernel supported. So if you're on Linux, if it's Android, or if it's an open embedded Linux implementation with PlayReady, for example, it should be able to use, of course, the same underlying mechanism.
So is this new ion heap type code available to look at somewhere?
Not at the moment. We're working on, it's being defined right now. We, in the security team, they have some code branches. And what we're waiting for is we're looking at the current effort to just get ion out of staging into the kernel. Once that is done, then we're looking to introduce this heap type.
Part of the reason I asked that was I'm working with Laura on doing the whole destaging of ion stuff effort. I was just wondering if someone from your team has actually looked at those patches and tried to validate or not.
I've been, Laura's been very active in this space. I guess she was at Connect. We had all of these discussions. I think she's been reinvigorated to get this work done, and you're going to be covering this tomorrow in your BOF. So I think that's really the place where people can get all those details. Again, us and some of our key members are very enthusiastic about getting ion out of staging. So hopefully it's not going to all just rest on the shoulders of a couple people, but more people will get involved to do this. Yeah. Thank you.
The memory you reserved for secure memory is static, right? You didn't look into dynamic.
Yeah, that's a good question. Initially, it will be static, like through the trust zone address space controller, designating region of memory as static, and then the SDP memory allocator will essentially manage that piece of memory. But it's something that we'd be looking to. It's been discussed that we could look at a more dynamic model for that. Okay, well, thank you very much for attending. I'm amazed kind of at this time. It's very nice to see this interest. Thank you.